All right, I think we have everyone here now. So I guess we'll just go in order from the schedule and attendance sheet. So that would put my team to go first.
Sorry about that.
McGuire, would you like to keep time for my team since I'll be presenting?
Yeah, I got you right now.
Okay, cool. All right, Brett, whenever you're ready.
Can everyone see this? You good? Okay. I'm good.
All right. We are Team Blue. Our final project is on facial recognition, specifically the security and improving its accuracy with neural networks. I'm Zachary Kirksey.
Breakout Plaza.
And I'm Brett Chapelier.
All right, so a little brief introduction. So as you all know, facial recognition is used in a lot of aspects of our lives. If you have an iPhone, then we all have the Face ID, which is used to log into iPhones or log into different apps. Another application for facial recognition is law enforcement. It's used to catch criminals through security cam footage, specifically for like store robberies and such. And then as far as social media goes, I know Facebook has a feature where you upload a picture and it will auto assign names to faces based on previous pictures and previous tags. Next slide, please. All right, so I'll go through a little bit of the history of facial recognition and neural networks. So for facial recognition, research started in the 60s with Woody Wilson. He came up with a way to classify faces through by measuring the difference between different focal points of the face. And this was increased to 21 facial markers to increase the accuracy. However, it's obviously not as good of a method as what we have today. In the 80s, the eigenfaces method was introduced, which is basically, it just creates a coordinate system for faces based on their eigenvalues and eigenvectors. And then the way you would match up faces is by measuring the distance between different faces in this coordinate system. And then in the 90s, the FARET program was created by the US government, started by specifically DARPA and NIST. And what this program is it basically just holds a database of facial images. And this database is used today by researchers to check the accuracy of their models. And then in the 2010s to present day, most of the research for facial recognition is in machine learning and deep learning. And as far as neural networks goes, in the 50s, the idea of a perceptron was developed, which is basically just the basic model of a neuron that we learned in class. And then in the 80s, this was expanded to a multi-layer perceptron, which allowed researchers to develop different neural network models such as convolutional neural networks, autoencoders, belief networks, and reinforcement learning. And then in the 2000s, the introduction of big data produced the need for deeper networks. Next slide, please. All right, so now I'll talk about some of the basic models. First, artificial neural networks, which we learned about in class. Obviously, this has a very low accuracy when just fed raw image data, because artificial neural networks, they'll do a great job of trying to find features in pictures when just fed raw unprocessed data. And then even with using interest point detection, which is basically like the early methods for classifying for classifying faces. The Harrison SIFT detector algorithm specifically give under a 30% accuracy, according to researchers from the Manipal Institute of Technology in India. However, it can be improved with other pre-processing methods. We'll touch on that later. Next slide, please. All right, and obviously we learned about this in class as well, the convolutional neural networks. These type of networks are much better at finding features and images. Accuracy is usually above 90% for different images and faces. And the highest accuracy for the IMNIS fashion data set, which is just an example of images, not exactly faces, but it did achieve a 96.91 accuracy when using the fine-tuning DART architecture. Next slide, please.
All right, so in this section, we are going to talk about accuracy improvement algorithms. So this section is divided into two parts. We have the pre-ENNs and the era of the ENN. So before deep learning, image processing and facial recognition was a very difficult task. So this is a picture of the workflow. So we have the input data, which was made into an N-by-N matrix. Then we have feature engineering and extraction. Then we have classification using any of the traditional machine learning classifiers. And then we have the output. So one of the major feature engineering and extraction techniques that was used to achieve this was the PCA, that's the principal component analysis. So the principal component analysis is a dimensionality reduction technique that is used to reduce dimensions of data by selecting the most important component, that's the principal component. It does this by projecting the data onto a lower dimensional hyperplane and then extract the features in a way to preserve the variance of the data. So even though we are reducing the dimensions of the data, we still preserve the variance of the data. So next slide, please. So in the next slide, it gives like a workflow of how we use PCA with
Sorry about that.
so how we use PCA with eigenfaces to achieve classification and facial recognition. So first of all, we start by creating a training set and loading it with the training set consists of M images, and each image is of the dimension n by n. We convert the faces into a phase vector, then we normalize the phase vector. So we normalize the phase vector by finding the average of the phase vector, and then we subtract the average phase vector from each phase vector. So by so doing, we are able to find the eigenvectors using the help of a covariance matrix. So after we find the covariance matrix, we have a large dimension of image. So therefore, we have to use the PCA to reduce the dimensions. And we do this by using a linear combination of the k-selected eigenfaces. Then from there, we are able to perform classification, either using the distance or different features. So the accuracy of this type of technique is about 75% to 80% accurate. And compared to what neural networks and deep learning can do this time, this is pretty low. Next slide, please. So with the ENN era, all the user has to do is to feed in the data, the prepared data, and the deep learning algorithm will figure out which features to use and how to learn, and then gives us the output. So one of the proposed model in this literature review is the next slide, sorry. So one of the proposed model is a multi-artificial neural network. So from the name, we know that it has different systems in the network. So we have like various deep learning architectures in the network. So the multi-neural network has 3 components or 3 stages. So first we have the M number of sub-neural networks. So from the image on the slide, you see the sub-neural network, the SNN1, SNN2, and SNN up to whatever number you want to use. Then the stage 2 has the collective vector that joins all the outputs from the SNNs. And then stage 3, we have the L number of CNNs. So after the SNN trains on the input data, we use the CNN to do further training and then classification, which improves the accuracy. So how the SNN is a 3-layered network. It has the inputs, which takes M number of inputs. That will be the number of features of the image. And there's a hidden layer, which is experimentally determined. And there's L number of outputs, which also serves as L number of inputs for the CNNs. So the training process, there are 2 phases of the training process. Next slide. So for the first phase, the SNNs are trained one by one, which is called local training, because in this stage, each SNN is given like a set of features. So let's say if we have 10 features and we have 5 SNNs, then if each SNN is given 2 features to train on. And then in the phase 2 of the training, which is the global training, they take input from the vector. They take input from the vector and it's trained on the CNN. So at this time, they've seen all the input data. So this stage is called the global training. So this model was tested on the Caltech database consisting of 441 labeled faces of 26 people and achieved an accuracy of 98%. So compared to what we could do earlier, this is like really high accuracy, even though it's not perfect, but it is like really higher than compared to pre-NNNs. Next slide.
Okay, so now I'll be going over some ethical concerns that people have over facial recognition technology. So it's pretty hard to sometimes weigh the pros and cons of using this technology. Some people and groups argue that the potential infringement on our freedoms is too great, and others think that the benefits that we get from this is worth it. There was actually a survey done across 26 countries that reported about 2/3 of adults support a limited and restricted government use of AI and facial recognition to maintain order. Less than 1/3 of them support a government use as much as needed, even at the cost of sacrificing their privacy. And less than 1/4 adults support a total ban of the technology. So it's not it's a pretty divisive issue. A lot of people have different opinions on it. And as far as like classrooms and stuff goes, in China, there was a pharmaceutical university that used facial recognition software for attendance and behavior monitoring of students. And so obviously the situation received a lot of backlash and concern, such that the Ministry of Education in China is now taking steps to curtail and regulate the technology. And then you also have companies like Megvii that are creating software that will track and analyze student behavior in class. Things like how many times you raise your hand, maybe you talk to your neighbor, or like if you lean over your desk. So this in turn could also be extended to teachers in the future and could mean that maybe they get monitored on a daily basis while they're teaching. And so obviously this could really change the dynamic of the structure of a classroom. And a lot of parents and teachers and students are concerned about this. And as far as policies and regulations go, the first city in the United States that made any law regarding facial recognition technology was San Francisco. And they banned the use of it for local agencies like law enforcement. And they argued that they had too many concerns over accuracy, bias, and privacy. After this, other cities in the US also passed their own restrictions or bans on facial recognition. And then in 2019, the US Senate also passed the Commercial Facial Recognition Privacy Act, which basically prohibits prohibits companies from using facial data without the consent of their users. And as I mentioned earlier, as far as international, China has taken steps to regulate the technology, and some countries in the EU have also done this as well, like Sweden. And now we'll go over a more secure model. And so basically, a server will store the images of each subject that's used in facial recognition. So when a client wants to access to the server about a particular subject, you will also need identifying features so that way the specific subject is able to be retrieved. But in an ideal secure environment, you would want the server to not have access to that specific information of the image. And you could do this through the use of encryption. So this proposed model uses LTPs, which are local ternary patterns. And these threshold pixels of an image in either three values, which are 1, 0, and -1. In that first formula, you can see below the image, the figure. That's how the image is actually that's how the image is actually grabbed. The M value is the neighborhood. The R is the radius at which LTP is performed. That value T that you see in both of those formulas, it's a tolerance interval between the central and neighboring pixels, which are denoted as P sub C and P sub N. And then that figure above shows the structure of what the model looks like. The keys, the public and encrypted keys, are generated with the values of N and G and mu and lambda respectively. And then once you get those keys, you can begin the encryption of a pixel. The encrypted Euclidean distance that you see, it basically will take an encrypted LTP query and a database vector, and then it will output those encrypted distances. To make sure that the correct vector that the client wants is obtained at the end over there at the top left, you basically have to get a vector of n encrypted distances. You need a smallest value in that vector, and then that will be compared with a distance threshold at the client side. So that way you maintain privacy between the client and the server. In the bottom left, you can see how they compared their model to other models that are used. They use two different databases, which are the ORL and GTF databases, which are publicly available. And as you can see, their results are bolded over there. You can see that they got the highest recognition rate for ORL and GTF respectively. And now these are division of responsibilities. Zach was in charge of neural networks, introduction and history. Peregrino was in charge of accuracy improvement algorithms, and I was in charge of ethics and security. And so in conclusion, through our literature review, we've researched the history of facial recognition technology, some of the applications it has in some basic models, also gone over improvement accuracy, improvement in terms of accuracy, and lastly, some ethical concerns, policies, and a more secure model that could be used. And these are references.
Any questions?
I think I stopped it.
Yeah, I actually have a quick question. So that security, the new type of security that you were just talking about, was that implemented after all the states were passing these laws and rules against facial recognition?
I believe it was during around the same time. I can't remember if they had a specific date that they started doing it, but I believe it was around the same time.
So are you thinking with better security and like encryption to kind of to keep that stuff safe, that laws will maybe ease up and allow for more use of facial recognition, or probably not?
I think it's possible, but maybe as encryption gets better, maybe hackers and attackers also get better tools to try and
Yeah.
bypass that. So
Okay.
I'm not sure.
I had a quick question. One of you mentioned about the multi-layer ANNs, where they had local and global training for the vectors and then the global for the CNNs. How long does that take? That sounds like it would take forever. You have to train one network and then train another network on a network's training. Your mic is muted. I could see you talking though.
And so with these architectures, it's mostly done by, big firms and big companies, and, they have these big GPUs and CPUs. So it takes time, but then it's like achievable.
Yeah, because it sounded because we were trying to identify numbers and like even that took 20
Yeah, I
minutes.
mean, I had AI class and we were trying to do the fashion eminence, and it took like days to run it. So yeah.
All right.
Anyone else?
If not, you guys did good on time, 18 minutes. So we could just move on to team face, Gabriel and Eric.
Cool.
Let me pull the slides up now. All right, can everyone see that? Cool. All right. Well, today we're going to be doing a literature review for the comparison and evolution of facial recognition algorithms with me and my partner, Eric. All right. So, introduction. Facial recognition is a technology that mainly is used for authentication. Obviously, the main purpose would be for, anything that really involves either really high security clearance or honestly just for a normal user who wants to feel a little more, I guess, secure. As its facial recognition is used to compare a digital image taken from a camera, obviously in real time, and compare it to one stored in a database in which an algorithm takes the two faces and compares them obviously differently depending on the algorithm. These comparisons are done through algorithms, and obviously as the years come, more and more come out and improve on each other. Actually, recently, some algorithms are using neural networks, as previously talked about. Today, we're going to begin with an algorithm called eigenfaces, which is the first complete one that was actually introduced. All right. There are three main goals when developing facial recognition technology. The first is obviously to protect the privacy of the users, as facial recognition does collect a massive amount of data. Obviously pictures of you, backgrounds, where you go to. Obviously, we want to protect those from not only, the obvious means like attackers and stuff like that, but also companies that want to gather your information and sell it off for a profit. Another would be obviously for easy integration to existing systems, such as improvement on other facial recognition systems or even just older authentication systems. And for the use of cheaper hardware, obviously we don't want to use the most sophisticated cameras every time. It'll be very expensive. And the third is obviously to achieve the best possible accuracy to make sure a constant verification is obviously achieved. All right. So if the objective of the paper is to investigate the evolution of prominent facial recognition algorithms, while also in the end comparing them and uncovering which has the best in performance and which have just kind of evolved off of other ones. For this presentation, we're going to be looking into eigenfaces, Fisher faces, tensor faces, LBPH, and open faces. All right. But first, before we can talk about any of the algorithms, we have to talk about the principal component analysis, or commonly known as PCA, which is a normalizer for the algorithms. Pretty much, PCA is a factor analysis statistical method, which is used for image recognition and compression. It reduces the number of variables that the algorithm uses and allows for the image to be normalized. So the algorithm always has a set, I guess, a set place to look for the focal points of a picture. Once the picture is normalized, the image is placed into a coordinate system that can be used by these algorithms to have kind of like have a normalized way of looking at the picture. Below that formula is the actual how it's placed into the coordinate system, with the two A's being the bounds of the image. The VI is called the eigenvector, which is where you find the focal points of a picture. And the lambda is the actual weights that are used to find the focal points in the picture. All right. Okay. So for the first one, it's going to be eigenfaces, which is the first one that was actually developed as a fully functioning facial recognition software. So obviously, once the PCA places it on the coordinate plane, the plane is then called in eigenfaces. It's called the face space, which is what that formula there is below, where the gamma is the actual image that is being compared. The U is the actual eigenvector, which was found in the normalization process, and the omega, which was the weight vector, which is the actual picture that is being compared to in the database. So pretty much once we find the, I guess, the ideal weight in which the picture compares most to, we then shift to another formula called Euclidean distance, which will then place the picture into the correct class, which will then allow the algorithm to correctly determine which picture in the database is the most comparable to it, which is the bottom formula. EK is the Euclidean distance, which is going to place it in the correct class. Okay. So for the results, the first row is the actual initial faces being placed into the algorithm, and the second row are a bunch of faces that are inside of the database, and these are the comparisons, the classes, if you will. So in the third row is our faces, like are the first row's faces that are conformed using the normalization process, and then a singular eigenvalue in which only the first face is the one that should be confirmed, which is why it looks like the most normal face out of the other two, which are very blurred and distorted to try to get a match. And the fourth row are the pictures conformed with 3 or more eigenvalues, which only, again, gives the correct value on the first column, and the other two don't pass. It is to be noted that the algorithm has around a 90% accuracy rate, but this is only in extremely ideal conditions, conditions such as extremely close-up pictures, lighting, and obviously the quality of the camera. All right. For the next algorithm, PCA is also used in Fisher faces to normalize the initial picture from the actual image. Once the image is normalized, the picture is then placed into a class scatter matrix, which is defined by that formula down there, where the only real notable thing to know is the SW is called the difference of classes, which is similar to the previous thing, but uses the matrix, which is essentially the difference, to find the actual class, and it gives a range of classes instead of just a singular class, which gives it a lot more leeway in finding a better accuracy and a lot more rough conditions of a camera. Once that difference of classes is found, the following formula is used, which is that one at the bottom, the SBV. Once the difference of classes is found, you just simply find the eigenvector again, and the same Euclidean distance formula is used to find the class, which will find you the picture. Okay. So for the results, as you can see from the pictures, when the initial picture is placed into the algorithm essentially breaks down the image like pixel by pixel until it finds a correct picture in the database. So the more distorted the picture in the more distorted the initial picture is, the more it breaks down until it can find a correct image in the database, which normally leads to a way longer computing time, but obviously a lot better accuracy. And as this is an evolution of eigenfaces, it still maintains the 90% accuracy, but in way better, or not way better, in poorer conditions. And with that, I'll hand it off to Eric for tensor faces.
All right, so facial recognition using tensor faces is based on a multilinear analysis of facial image ensembles. These are acquired using a higher order PCA. Once the facial ensembles themselves, the D, it's made up of a core tensor Z and then multiple parameters that are matrices, the number of subjects, viewpoint, illumination, and expression parameters. Next slide, please. So the facial recognition algorithm performs a decomposition of the ensemble to extract the people matrix. Once this matrix is acquired, it contains row vectors of each person, and you can construct a basis vector or a basis tensor B, which can be used to obtain a particular viewpoint, illumination, or expression. The base or tensor B can be flattened and compared against unknown facial images, and that's how you identify the person. Next slide, please. So using multilinear analysis on tensor faces yields a significantly better recognition rate than standard eigenfaces, since it can withstand better or differences in viewpoint, illumination, and expression, which is something that eigenfaces struggled with, because for eigenfaces you have to be directly front facing and it has like the lighting conditions have to be good and everything. Next slide, please. So here you could see some of the ensembles. It breaks it down into the people, the viewpoints, the illuminations, and the expressions. They look similar to eigenfaces, but they account for different viewpoints, illuminations, and expressions. Next slide, please. So the next algorithm is the local binary patterns histogram, LBPH. It's one of the oldest and most popular facial recognition algorithms. It's relatively simpler than the other facial recognition techniques. So there's 4 parameters that are used when you're using this algorithm. They're the radius and neighbors, which are going to be used during the LBP operation, which I'll talk about in a bit. And then there's also the grid X and grid Y parameters, which are used to divide the image into sections, which we'll also talk about in a bit. The algorithm first assigns an ID when it's training on a set of images to each image, so it knows who the image belongs to, which it then applies the LBP operation to the training images, which it highlights important facial characteristics using something called the sliding window technique. After the new image is gathered, it is divided into regions using the grid X and grid Y parameters. And then you're able to form a histogram based on the intensity of the images for each region. These histograms are then concatenated onto each other to make one large histogram for the entire image. And then this basically is what describes the image. So when you have an unknown image, you do the same process to get a histogram for that image, and then you simply compare it against the other histograms that you have stored, and you find the one that's the closest match. Next slide, please. So OpenFace is a deep neural network, like a toolkit to run facial recognition. It uses PyTorch, and it's trained on over 500,000 images. And the creators of this toolkit also said that as the dataset continues to grow, this will get more and more accurate. It's one of the first open source tools that includes major things such as facial landmark detection, head pose estimation, facial landmark tracking, eye gaze tracking, and more. Next slide, please. So this is just a comparison of some of the algorithms that we went over. Eigenfaces was one of the first ones that was developed, LBPH after that, and then Fisher faces and tensor faces were both evolutions of eigenfaces, but they both are improved upon it in different ways. And then OpenFace, which it came out just recently in 2015, uses deep neural networks to run facial recognition. Next slide, please. All right, so in conclusion, facial recognition has been in development since the mid-60s. There have been many algorithms that have been made to improve accuracy and the computational complexity of these. Eigenfaces is one of the oldest facial recognition algorithms and has been used as a stepping stone for other algorithms such as Fisher face and tensor faces. These algorithms have built upon each other to improve accuracy under different circumstances such as view, emotion, lighting. With deep neural networks, even more is possible. Facial recognition with non-frontal views and uncontrolled data becomes possible, and deep neural networks should be seen as the future of computer vision and machine learning for facial recognition and should continue to be developed. And then next slide. And these are references and any questions. All right, well, if there's none, thank you guys.
Yep, appreciate it.
All right, I guess we can move on to a third group, which is Team Super.
Yep, that's us.
Oh, also, y'all were fine on time.
Sounds good, thanks.
All right, so my name is Julia, and Patrick and I are going to talk to you guys about the detection of cyber attacks using artificial neural networks. So this is just our little agenda, what we're going to be doing. You can go ahead and go to the next slide. So just a brief overview. So artificial neural networks have become an emerging trend as a form of cybersecurity over the last few years. Cyber infrastructures are only continuing to grow and more data is being shared through them. So with this, new methods of security have become a necessity to protect all the data that is being shared and transmitted from cyber attacks such as DDoS attacks, unauthorized access, phishing attempts, service misuse, things like that. So these cyber attacks are detected through methods like supervised and unsupervised training algorithms, online and offline learning, and many others. And ANNs are constantly evolving and becoming more and more accurate with the detection of cyber attacks due to the training methods that are used on them. So we're just going to go ahead and dive deeper into some of that in this presentation. So next slide, please. So what are artificial neural networks? So ANNs are intelligent programs that are able to mimic the behavior of the human brain so they can possess qualities such as pattern recognition, learning ability, contextual information processes, and many more. And they're only continuing to advance to solve issues related to these qualities. So the goal of ANNs was to create an intelligent program that's based on the human brain and how our neurons signal one another. So this definition I have here on the screen is from IEEE Circuits and Devices magazine article, and it says that inspired by biological neural networks, ANNs are massively parallel computing systems consisting of extremely large numbers of simple processors with many interconnections. So some of these desirable qualities that ANNs do have that relate to the human brain and how our neurons do interact include massive parallelism, learning ability, adaptability, inherent contextual information processing, and many others. Next slide. So the structure of an artificial neural network consists of 3 layers. It has the input layer, the multiple hidden layers, and the output layer. So each of the layers have a number of artificial neurons in it, or these are also called nodes. So the input layer receives information and signals from the outside environment. And then data can be sent to the next layer of the network based on the threshold value of the node it's passing to. So these nodes have assigned threshold and values and weights already assigned to them. So if the output is above the threshold value, data can be passed. If not, it cannot be passed. So the hidden layer consists of neurons that extract or process the patterns from the input data. And then the last layer is the output layer. So this produces the network outputs or the result from all of the process information in the previous layers. So there are 4 main types of artificial neural network structures based on their interconnections between the nodes and the networks of layers. So there's the single layer feed-forward network. So that's that first picture you see in the top left corner. This is where the ANN has 1 input layer and 1 output layer. So the information goes right from input to output. And this is the simplest kind of ANN architecture. Next is the multiple layer feed-forward architecture. So these have multiple layers of hidden neural layers or networks. These type of artificial neural networks are used to solve issues relating to function approximation, pattern classification, system identification, and so on. It's used to solve a very diverse group of issues. Next is the recurrent or feedback architecture. So this uses the outputs of the neurons as feedback for the inputs for other neurons in the ANN. And finally is the mesh architecture. So ANNs with this architecture produce outputs with the consideration of previous outputs. So this is a unique one because the location of the neurons is directly related to the weights and thresholds in or like of the neuron. So this ANN is commonly used for things like pattern recognition. Next slide, please. So all the types of ANN architectures mentioned in that previous slide are used to detect different cyber attacks. ANNs have the ability to recognize events and behavior that are not typical and identify that as potential threats and solve the issue without any human interaction even needed. So I'm just going to dive into some of the main types of cyber threats and how they're detected by ANNs. So the first one is DDoS attacks. So ANNs are trained with a variety of real DDoS attack cases to continually increase their ability to recognize them in a real world setting. So it's extremely important for this to not use repetitive or any pattern-like training methods, so the ANN can be prepared for all types of DDoS attack scenarios, not just certain ones pertaining to particular areas. The next is intrusion or service misuse detection. So ANNs are trained with normal user activity, but also trained with attack patterns. This way it has knowledge of what both are supposed to look like, the good and the bad. So when there is a deviation from that standard of normal user activity, it can be identified, flagged, and then dealt with before the situation escalates. And then finally is phishing attempts. So this is arguably one of the biggest security issues nowadays because of how real these attacks look. They're able to trick users very easily. So ANNs combat these by training recurrent ANNs that I mentioned earlier in the PowerPoint to identify the phishing attempts through URLs. So the ANNs trained to evaluate the URL, go to the site, evaluate that using algorithms that it has been implemented with in training, and then determine the safety of the site from there. So next, Patrick is going to dive into more about how the ANNs are trained to detect these cyber attacks.
Is my mic on?
Yeah, I can hear you.
Okay. So ANNs have to be trained through learning algorithms. They can't just have all the data just plugged right in. So, and there's no like tweaking numbers manually because it's a ton of weights that you just can't program it manually. So most learning algorithms work with a large sample data set. The more data you have, the more real life cases it'll probably work for. So the first thing it does is it splits the sample data into training data and testing data. If it was able to train on all of the data, then it would eventually be able to learn the whole set, and it would trick you into thinking that it's learning the problem, but it's actually just learning every single individual thing you put in. So by separating it, it never learns the testing data. And so every time you test it on the testing data, it's never seen it before. So it's just like if it's the real world and you get a real idea of how fit it is. So what a learning algorithm does is basically it takes all your data and it tries to increase the ANN's fitness as high as possible. Most of these learning algorithms take place in epochs, which is basically like one full use of the sample data. And after a certain number of epochs, or after fitness gets high enough, the ANN is considered trained for use in the real world. So the first type of artificial neural network is the supervised learning learning method. What was it called? Yeah, supervised learning algorithm. So what that does is basically every training data has an input and an output, and it compares what the ANN thinks the output is to the real output, and that makes an error. And from that, we adjust the weights. Unsupervised learning, there is no known output for the input. So we take the output and give it some kind of score, which we'll call the confidence, and then use that to adjust the weights instead. Reinforcement learning is similar to supervised learning, but the way that we adjust the weights might be random or stochastic, or it might change over time in order to like get it as good as possible instead of just repeating the same process over and over again. Offline learning involves not adjusting the weights every time and instead accumulating a bunch of errors on top of each other and then trying to fix them all at once. This is technically more parallel because we can train through like the whole data set in parallel at once, but it's usually like slower because the errors will compound and may clash with each other, and you don't get the best change to the weights from all of them combined. Online learning is just the opposite of that, which is like treated as the default, where every time we put a sample through, we adjust the weights. Simulation-based learning is somewhat similar to offline learning because it goes through a whole series at once, but the series is like continuous time stuff. So in other cases, we might have a simulation with like physics simulation with a robot walking, but in this case, it would be more similar to time series simulation, and it would be scored based on its confidence and when it raised alarms for a DDoS attack. And that's similar to offline learning because you can't really score it until you've seen the whole simulation play out.
Okay, so although artificial neural networks are becoming increasingly popular as a form of security for cyber environments, there are definitely still some vulnerabilities that exist within them. Two of the biggest are unstable predictors and the ability to fool ANNs. So unstable predictors just means that like one small change in the data that's used to train and build the ANN can result in a very different outcome than intended. So this is an issue because ANNs that have almost identical training methods, but maybe just have one minor difference from one another, can result in two different ANN models. And these different models can lead to very different performance for things with similar data. So obviously this can become an issue because there will be big differences between data that's not so different. So that can lead to detection within or errors within detections. And the next is the ability to fool ANNs. So ANNs are very intelligent systems, but there are definitely still some ways to trick them. So this is done by placing what's called noise to fool the ANN. And it just kind of makes it produce the outcome you want. So these types of attacks can also be known as black, white, or gray box attacks. Attacks determine the level of noise that's needed by the hacker to create the desired outcome. So this picture I have on the screen is a really good example. So this is actually the same picture, but one of them has a certain amount of noise added to it to make one look like a cat and one look like a dog, when originally these were the same picture. So it's just an example how noise can kind of trick the ANN into giving you what you want. So this model really is really dangerous because it's also very hard to identify this type of attack, since it's not necessarily breaking an ANN, but kind of just changing that outcome. Next slide.
So in conclusion, over the last few years, the use of artificial neural networks to protect cyber environments from cyber attacks such as DDoS attacks, service misuse, and phishing attempts has become an emerging trend. Yeah, the cyber protection space is like somewhat new to the internet, but you know, ANNs are also somewhat new, and they are pretty good at defending against them, especially because hackers can just get around the system that they know how it's implemented. If they see an ANN is doing something, they don't necessarily know how it works. ANNs are specially trained using a variety of methods such as supervised or unsupervised learning, online and offline learning, and others like simulations and reinforcement learning to continuously improve their accuracy of detecting these cyber attacks. Yeah, with a handwritten system, you immediately get the kind of results you expect, but with a ANN, you might need to look at the training methods and change them, and maybe look at the training data you're using. There's a lot of variables that go into making sure ANNs have good accuracy that you don't necessarily need for traditional methods. There are still some vulnerabilities that exist within these forms of security, but with continuous research and training of the ANNs, this intelligent security method will only continue to grow and improve. Yeah, since ANNs are kind of trained by themselves, we don't necessarily know all of the vulnerabilities that we're putting into them. So like the noisy cat looking like a dog, it's hard to know what will be the vulnerabilities in the systems until they get through. But like everything with ANNs and deep neural networks is improving, so hopefully that'll improve too.
So here's just our division of responsibilities, and then we have our sources after that, and that's it for us. So does anyone have any questions?
Yeah, I was kind of curious, what kind of data gets put into the ANNs for like DDoS attacks? Is it like time series data? Is it like basically like the amount of traffic? Like what?
Yeah, so it's definitely amount of traffic, because DDoS attacks are typically, they're trying to overwhelm the site they're going on. So they literally take that data of the site being overwhelmed and put that into the training method. So they're like pulling from real examples of this happening previously, and putting it into training to give that actual effect of what will really happen.
And also, what accuracy do these models obtain?
Patrick, I feel like that's more of a you question.
I think in the first paper I looked at, it said they had one that was like 90% accuracy or 93%.
Any other questions? Thanks, everyone.
You guys were good on time, by the way.
All right. I guess my group will get started. Hopefully we finish out before 6:45. Just a second while I set it up. You guys see that all right? All right. So my group will be presenting artificial neural network assisted electric load forecasting. And my group members are myself, Akil, and Michelle. Now, as I'm sure you remember from our proposal, power generation is basically the backbone of the world. Without power, businesses can't function, people can't relax, and cities and states collapse. Ideally, power is endlessly generated and demands are always met, but that's not going to happen. And that's why we need to understand how much to generate and when. This is why forecasting these loads is important. If someone were able to accurately predict how much power a group of people would need, they could generate it and no excess is made or wasted. That sounds hard to do reliably. So that's why load forecasting is essentially broken down into three major timeframes: the short term, the medium term, and the long term. Short-term forecasts usually assist generators and markets and are therefore best for times between minutes to even a week. Medium term is usually best for operations planning, like when a generator might shut down for maintenance. And it's best used from a couple of months to a year. Long-term forecasting is primarily used to develop new power grids and expand those power grids. So that's why they're usually over 1 year and even up to a decade. And now that my group and I have taken the time to further our research, I'm ready to tell you the reality in the future of what electric load forecasting using artificial neural networks is. Something that I found very interesting when I was conducting my research was that there exists the very short term forecasts that are actually needed within minutes and not within hours or within days. So this paper by Wichter and Moshe gave a proposal for an approach to this type of forecasting. They argue that the modern day power market was extremely competitive, where everyone's trying to make their profit and are constantly undercutting each other to get the upper hand. And to participate in this game to get the higher profits, one would love to be able to have forecasts instantly so that they can provide the best bids and the best offers to the market as quickly as possible. This group applied multiple single hidden layer ANNs to the process so that they could actually get this forecast within minutes. This model was particularly interesting because while you would expect a load forecasting ANN to be trained on loads, this one was actually only trained on temperature, time, and percentages. Historical load data for short term is not usually available because the data is not properly indexed, labeled, described, or whatever ANN needs the data to be. But the researchers noticed that if a day has a similar temperature to another day, while the power might not ever be the same, the percentage that power changes will be the same. You can see on the right-hand side and the top chart that the power levels between one day and another, the solid line is one day and the dashed line is another. While that power is never at the same level at any time, the bottom graph shows that the increments that the power will be seeing is almost identical. So they were able to implement this somewhere in the United States, the paper didn't specify where, by dispatchers for online load forecasting, for very quick forecasting, basically. And it was able to learn load dynamics without memorization and could perform all future load conditions with a very high accuracy. When it was implemented, it gave the dispatchers a prediction for loads with a maximum of a 1% error. In addition to that very small error, it had a 66% reduction in training time from their traditional forecasting models. And now that we've seen what the very short term holds, we can take a look at the regular short term. This is mostly important for secure operations of power systems, as precise forecasts can result in cost savings and optimized prices. When using an ANN for short-term loads like this, a few inputs are usually taken into account. Time indicators like the current hour a day, weather-related inputs like wind velocity or temperature, and the historical loads. In this paper, historical loads were once again not used because they're just not available, but instead estimations of historical loads were used. And only temperature again was used because that has the biggest effect on power compared to things like wind or cloud coverage. So this paper decided to use a feed-forward ANN with hour, day, and estimated temperature inputs, and it was actually implemented in Quebec. So this neural network took in the time, the day, and 3 temperature measurements for 10 locations over the entire province for a total of 32 inputs. It was trained on alternating weeks of a month and tested on the weeks that it skipped, and it used backpropagation and the Levenberg-Marquardt algorithm to adjust its weights so that it can be used at any time of the year. It works similar to the very short-term model, mainly using temperature to predict the loads. And as seen in the figure on the right, this kind of prediction is great for short-term The actual load and the ANN forecast were incredibly close, seeing a maximum error of 0.98 over 72 hours. I don't believe this model was actually implemented. I think it was trained on old data, but it certainly shows hope that this could be a reality. So now that you know what very short-term and short-term load forecasting looks like, we can just discuss some quick applications that I saw. We talked about the very short-term at a power utility and the short-term at in Quebec, but there are actually multiple other applications. Further research found the short-term load forecast used in Elam, a western region of Iran, that used historical loads for a day-ahead forecast, which usually ease the tensions that a traditional forecaster needs. If they have a second baseline to go off of, it's probably easier to predict. And as seen again in the top right figure, the ANNs predict very close to the real forecasters. Additionally, a CNN was used in Romania just last year to diminish the effects of COVID-19 on the grid. And you can see in the bottom two figures, power usage plummeted. So when they put in the CNN to kind of boost, kind of help them understand when power will be used, I think they were able to get a good result, but the data set was super ambitious. It needed time, historical loads, even the pandemic conditions. This was also used in Kuwait using weather data, similar to how the short term and the very short term used. And they were actually able to predict loads over a day basis as well. And now we can move on to medium-term load forecasting.
Hey everyone, my name is Zakir Ahmed, and since this medium-term load forecasting is brand new in terms of artificial neural networks, so I will first deeply discuss about it and the current model that they are using to forecast this data, and then I'll move on artificial neural network and whatever result they got since now. As Maguire talked about, medium forecast it goes from week to an year, and it is very important for utility companies to know what could be their load in future, so they can better plan power generation expansion or schedule maintenance or perform system improvement, and it also helps to decide the cost of their fuel, what they are going to use. Medium and long-term load forecasting has not been studied as extensively as short-term load forecasting. So medium-term load forecasting categorizes the methodologies for modeling into two general groups. The first group focuses on economic analysis, management, long-term planning, forecasting of energy, load and energy policies. The second approach basically uses the past monthly load weather information. This modeling approach is more suited for stable economies. So different methods like day approach, various regression method models, time series, neural networks, statistical learning algorithm, physiologic and expert system have been developed for short-term load forecasting, but for medium and long-term, there are not many methods they are using. The most common are like end-use and econometric approach that is still currently used in different areas, and in some of the areas they just mix both approaches and implementing it. The end use, it is sensitive to the amount and quality of end use data. For example, in this method, the distribution of equipment age is important for types of application. End use forecast requires less historical data, but more information about customer and their equipment. And the econometric approach combines economic theory and statistical technique for forecasting electrical demand. The approach estimates the relationship between energy consumption and factor influence consumption. These traditional models are limited and sometimes might lead to unsatisfactory solution. The reason is too high number of computational possibilities, leading to large solution times and complexity of certain nonlinear data pattern. Hence, machine learning and artificial intelligence-based technique provides promising and attractive alternative results. Next slide, please. The artificial neural network approach was discovered in 1990s by Warren and Walter as an alternative mechanism to the time series forecasting. Artificial neural network model have been used and studied in recent years for electrical load forecasting and gained huge popularity in last few years. Basically, the neural network is a nonlinear circuit that is capable of doing nonlinear curve fitting. The commonly employed model that they are even implementing or testing in different areas are like feed forward NURBS, back propagation, radial basis, the random and recurrent and self-recognized measure. And the next slide, please. I just found a couple of examples. I will just discuss two of them. The Taiwan power company, they just tested their dynamic artificial neural network, and when they forecast their data, and the result were really surprisingly, because the error they had in their forecast was less than 1%. And the Bruce County in Canada, they basically done a study, and they basically implemented different neural network algorithm, and the chart is showing their computation time and how much the mean or root mean square error they had. And these kind of results, just it's kind of motivation for in a research area to replace a traditional model with an artificial neural network or different advanced technologies, so we can improve we can improve medium or long load forecasting, like they have done a great job in short time load forecasting. And next slide.
Hey guys, I'm going to be talking about long-term load forecasting, which is basically load forecasting from a year and up. Long-term load forecasting is important because either overestimation or underestimation of power consumption can cause increases in the building of electric systems and operating costs of facilities. Overestimation of long-term load forecasting can lead to excess supply and not enough demand. And underestimation can lead to failure in providing enough power to consumers and can mean high cost when units are working at their peak. Both over and underestimation can directly affect consumers by driving up their utility bills. This is really bad for us because it dominoes into the economy. Long-term load forecasting is also important because it is used for the planning and operation of future power systems or power system expansions. And accurate forecasting will either increase or reduce the unit building and operational costs for power generation, transmission, and delivery system facilities. Power system expansion planning takes into account whether the existing capacity is enough to meet the projected demand, what type of subsystems are needed, and the capacity the subsystems must have to meet that projected demand. Planning for future power systems takes into account the projected population of what type of plant will be needed, and the capacity of the plant. This can drive long-term financial planning for cities and towns and their economic development. Next slide. Again, it's really important that long-term load forecasting be as accurate as possible. Some challenges to long-term load forecasting are, one, the certainty of the inputs, and two, the efficiency of forecasting models. This is why we turn to the help of artificial neural networks to assist with long-term load forecasting. One common method is the feed-forward artificial neural network model, which makes it so that there is no need for a forecaster to have a clear-cut understanding of the relationship between input and outputs. Because of the simplicity of feed-forward ANNs, it is important to pre-process inputs by, one, cleaning the collected data to see issues in the raw data and remove them when considered bad data, and two, the remaining data should be stored and missing data should be refilled. Not doing this would affect the long-term load forecasting's accuracy. The picture on this slide is a good picture of feed-forward artificial neural networks. Another type of ANN used to help LTLF is deep neural networks, which use more hidden layers and have more flexible structures than feed-forward neural networks. DNNs are more complex, they're harder to train and require larger amounts of data, load data for larger amounts of time. Otherwise, the ANN would generate invalid outputs after training. But DNNs can manage numerous sequences though, and large image data sets. I want to point out that data used by ANNs to forecast should be normalized to give each input an equal weight for the start of the training phase before continuing on to the validation phase. In long-term load forecasting specifically, input magnitudes can vary from thousands to billions, So if the data was not processed beforehand, the artificial neural network would place higher importance on inputs with higher magnitudes, while disregarding the effects of other inputs with smaller magnitudes. Next slide, please. In long-term load forecasting, forecasting can span from, again, 1 year to many years. So there are inputs such as weather indicators that can be much less accurate due to their obvious nature throughout their years. These weather indicators are those like temperature, humidity, and wind speed. The first example I want to talk about is an LTLF supported by artificial neural networks used to create a load forecast model for the New England power system. They split their inputs into two types. One was the heating degree days, or HDDs, which are the demanded load on days that were cold, and cooling degree days, CDDs, which were the demanded load on days that were really hot. The other input was the historical record of energy. In the picture, for each month of targeted forecasted energy, the model used HDDs, CDDs, and historical data of the same target month of 11 prior years. In picture 2, the green color is the historical data from 2000 to 2011. The blue color was the monthly energy during January 2011 to March 2014, used to train the forecast model. And the red color was a validation set for April 2014 to 2016. The ANN had low forecasting errors for the training and validation sets. Another example, and sorry if I pronounce this wrong, Waleda Soto Town, Ethiopia, used 9 years worth of data to basically forecast the electrical load of the town for 6 years into the future. Their long-term load forecasting used ANNs, and it demonstrated that the electrical load consumption of the town would increase from 13.568 MW for 2017 to 22 megawatts for 2023. Data like past electrical loads, population growth, and GDP were used as inputs for the artificial neural network. And finally, in Indonesia, there is a company called PTPLN, which is a state company, but basically conducts planning to develop electric infrastructure for 10 years at a time. They use DNNs to forecast the load demand in Bali using historical data from 2004 to 2018. They use factors such as existing load consumption conditions and other typical inputs used to feed artificial neural networks. Different from other studies we reviewed, they took the usage of renewable energy generation as an input, which can affect the load demand because renewable energy is intermittent power and is power and is intermittent power and its power is power that is mostly supplied at noon. Next slide.
All right, that's the end of our presentation, but in conclusion, you can see that ANNs are pretty much present in all fields of electric load forecasting and hopefully continue to be present in all fields. The need for accurately forecasting when you'll need power and how much you'll need power is pretty much going to only get more demanding as we develop more power methods or power storage methods. But if anybody has any questions, these are our references that we used. And that's the end of our presentation.
Yeah, we're good on time.
Yep. But you know, if there aren't any questions, after all, it is 6:46. Class is over.
Night, everyone, if there's no questions. Nope.
All right. Well, thanks everybody. I'm glad we all got in under time. We all had a good presentation to listen to, and hopefully, Professor, if you're watching this, be nice. Thanks, guys.
Thanks, guys.